So let's just take a real quick look at a isolated moving rod in a magnetic field. If we say let's look at the forces on some positive charge inside of this rod, well, we know that the force is going to be equal to the charge velocity crossed with the magnetic field, and we can see that this positive charge is going to feel a force in the upwards direction. So we'll end up with a net positive charge at the upper end of this rod and a net negative charge at the bottom end of this rod. However, really having a separation of charges, that's also a potential of voltage, and what gets set up is going to be an electric field. This electric field is going to give a force on this proton, or this positive charge in the rod, that's actually going to be in the downwards direction and equal to the charge times the electric field. Now, essentially, it's going to balance the magnetic force out. So we could say that the charge multiplied by the electric field is going to be equal to the charge multiplied by the speed multiplied by the magnetic field, and those charges are going to go away. So our electric field is simply going to be the velocity multiplied by the magnetic field. Recalling that the voltage is equal to the electric field multiplied by some distance of separation, it's going to be the length of the rod. You can see that the voltage induced on this rod would have to be equal to the velocity multiplied by the magnetic field multiplied by the length of the rod. Now this looks very similar to the induced EMF if we were to take this rod and connect it up with kind of its components that we've already talked about in the previous couple of slides. That induced EMF is going to be also related to the velocity, magnetic field, as well as the length. This is called motional EMF, and Lenz's law is going to give us the direction, which would be in the counterclockwise direction, opposing the change. So I've talked about changing magnetic flux largely by changing the area. However, keep in mind that we can also change the magnetic flux by changing the magnetic field. Consider a case where if I have a current flowing through a wire and I wrap it around a rod creating a solenoid, you can do the right hand rule, convince yourself that the magnetic field has got to be pointing in that direction. We insert this solenoid into a larger wire loop, and as long as that current is constant, and this magnetic field is going to be constant, and we're going to have no induced current on this outermost wire loop. However, as soon as we start to change that current, we have a changing current with time, then we're going to have a changing magnetic field. That's going to induce a current on this outermost wire loop. Now, we know that we can write the induced current or induced EMF to be the change in magnetic flux over some change in time, but let's just think for a minute. What causes the current to flow? Well, what causes the current to flow is going to be the presence of an electric field. So we could rewrite this EMF, rewrite Faraday's law to say that we're going to create some electric field, and we're going to find that electric field by looking at the circular integral of this electric field dotted with dl. So let's take a quick look at a real-life application of this, thinking about a metal detector that you go through in an airport. Essentially, the way that guy works is it's going to have a current running through a wire. It's going to essentially have a magnetic field going through it, and then we go ahead and we change that. That's going to change the magnetic field. On the other side, we're going to have a receiving coil, and that one essentially knows what magnetic field it should be receiving, and it knows what current it should be receiving. If someone were to go into this metal detector and have in their suitcase something that is metallic, what's going to happen is it's going to induce an electric field, and have a force, induce a current inside of this fellow's briefcase that's going to oppose the changing magnetic field. Then we have a flowing current that's going to set off its own magnetic field, and that's going to cause this current over here to be different than what we would expect it to be. Kind of a technical name for that is going to be eddy currents. Metal detectors that you have on the beach essentially are going to work the same way, except for the receiving coil and the primary coil are both inside of the metal detector, as you can see right here. Now that we've covered Faraday's law, we're essentially going to wrap up everything we know about electricity and magnetism in a neat little package and call that Maxwell's equations. But before we do so, we need to revisit Ampere's law from chapter 28. So it's going to be a fairly important slide right here. It's going to be kind of an addendum or correction to Ampere's law. Thinking about Ampere's law, if we had a wire in a circuit that was, had some current flowing through it, then we could, draw our path for Ampere's law, do the circular integral, and figure out what the magnetic field is. However, we have to kind of ask ourselves, well, what happens if we have a current carrying wire in a circuit that's going to go through a capacitor right here? That's essentially a break in the circuit, and there's going to be no current right there. Well, let's just say, well, if we were to go ahead and measure a magnetic field around that capacitor, it turns out that one is going to exist. So we're going to have a circular magnetic field just like we have shown right over here. Well, how does that happen? Let's just think for a second about what drives this current right there. What drives that current is going to be an electric field. That electric field is going to cause more and more and more positive charge to accumulate on that plate over time, and more and more negative charge to accumulate on that plate over time. So what we're going to have is we're going to have a changing electric field inside of that capacitor. So what we have to do is we can define this displacement current to be equal to epsilon naught multiplied by the change in electric flux over time. Essentially what that's going to do is we're going to have our circular integral of magnetic field dotted with dl. We're still going to have our mu naught and I enclosed, and now we're going to say if we have a break in a path but we have a changing electric flux, we're still going to get a magnetic field. So we're essentially just kind of tacking on this little idea of displacement current into Ampere's law. So this leads us to finally say we know everything that we need to know about electric fields and magnetic fields, and we can essentially write probably the most important set of equations for this semester, Maxwell's equations. It's going to consist of Gauss's law for the electric field, so that guy right there, Gauss's law for the magnetic field, and then Ampere's law and Faraday's law. Note that Ampere's law has this little displacement current correction that I mentioned on the last slide. What we can kind of see right here, let's just take a look at the last two equations, is we're going to have the magnetic field being essentially due to some changing electric field over time. We're also going to have the electric field being due to some time rate of change of the magnetic field. What this means is if we have a changing magnetic field, it's going to cause a changing electric field, and yet a changing electric field is going to cause a changing magnetic field. So really this is going to form the basis for electromagnetic waves, which consist of a changing electric field and a changing magnetic field. So we're going to take a very brief foray into chapters 30 and 31 and talk about inductors and transformers. Essentially, if you remember from chapter 29, I just covered that the induced EMF is going to be related to some time rate of change of magnetic flux. And when I talked about Faraday's law, we had two coils of wire, one of which was inducing a, well, I said electric field at the time in the other coil of wires. Now we're just going to talk about it in terms of voltage and current. So if we have a coil of wires, it's got some number of turns to it, and if we run a current through this coil of wires, then it's going to establish a magnetic field. How much magnetic field is going to depend on how many turns this coil has, as well as how much current is flowing through that. Now suppose we had a secondary coil of wires that were that was inside of this magnetic field, then we're going to essentially have some magnetic flux on coil number 2. What would happen if we went ahead and we started to change this current? Suppose we were to increase this current, then we're going to have a changing magnetic flux in my secondary coil. So essentially going to be inducing a electric field, but also inducing a current and inducing an EMF on this second coil of wires right here. Note that the Lenz's law would give us the direction. If we were to increase I1, increase the flux, then I2 is going to essentially try to oppose that increase. It turns out that we can also have an inductor induce itself, if you will. An inductor is essentially going to be just a coil of wires. If you go ahead and you open up just any circuit board, you might see something that just looks like a coil of wires, kind of like you're seeing down here. That is essentially what we call an inductor. And essentially what this guy is going to do is going to play games with magnetic fields and electric fields. If we were to hook a coil of wires up to a circuit, get some current flowing through this guy, then at the end of the day we're going to have a magnetic field, a fairly strong magnetic field, flowing through this circuit. Suppose now we were to suddenly cut this wire right here. Well, all of a sudden there's going to be a large change in magnetic field. Remember that EMF is going to be equal to the negative time rate of change of magnetic flux. So we're going to have a changing magnetic flux, so we're going to have an induced EMF on this guy, and all of a sudden this magnetic field is going to get smaller and smaller and smaller and smaller, so we're going to induce a magnetic field that's going to oppose that, so the induced magnetic field is going to be in that direction, and so we're going to have some induced current some induced current. We can describe this kind of mathematically by saying that the self-inductance is going to be equal to the number of coils multiplied by the flux, magnetic flux through that guy, divided by the current. Let's just take a very quick look at what the potential would look like across an inductor inside of a circuit. Let's take a quick look here. Suppose we have just a simple resistor. We have some positive terminal and some negative terminal. We have current flowing across that guy. We can see, for a very simple resistor, that the voltage at B is going to be less than the voltage at A, more or less because this resistor has gobbled up some of that potential. Now let's take a look at an inductor in a circuit. Inductors are going to look like little coils of wire. If the current is going to be constant, then the time rate of change of the current is going to be equal to 0, and in that case an inductor is not going to cause any potential difference across it. So the voltage at A would be equal to the voltage at B because there is no change. So the inductor is not going to cause any EMF. Suppose, however, we have the current flowing through an inductor and this current is changing. What that means is if the current is increasing, we're going to get some back EMF pointing in that direction because it's going to oppose the change, and so we're going to end up with the voltage at A being larger than the voltage at B. Similarly, if we have some current flowing through an inductor and it's suddenly decreasing, well, the inductor is not going to like that very much, and so it's going to have this back EMF that's going to be flowing in that direction, and we can see that the voltage at B is going to be now larger than the voltage at A. Keep in mind that this induced EMF isn't going to oppose the current, but it's going to oppose a change in the current. And inductors are going to store energy in them, much like a capacitor stores stores energy in the electric field. Essentially, inductors are going to store energy, so that got in the magnetic field. And how much energy it stores, well, that's going to be related to how much self-inductance it has, which is related to the current flowing through it and the number of coils, as well as the current that is flowing through it squared. So now let's look at a more real-life application for this, transformers. Essentially, what transformers are going to do is they're going to allow us to transmit electrical energy without two circuits actually touching. So suppose I had some coil of wires around a magnetic core and I have an alternating current source. What that means is if I were to look at my current as a function of time, then the current is going to become positive and then negative and then positive and then negative, so a constantly changing current, well, what that means is the current's going to set up a magnetic field inside of this iron core. Changing the current means we're going to have a changing magnetic field. This secondary wiring, that's going to all of a sudden start getting an induced current on that because the magnetic field is going to be changing. Now, it turns out that the voltages are going to be related to the number of coils. So a very important set of equations to keep in mind is we're going to have essentially some primary, our input, and then we're going to have our output. We're going to be putting in some primary voltage. It's going to have some number of coils. If we wanted to have the voltage be different at this end over there, then we just have a different number of coils. If we want to step up the voltage, then we go ahead and we have more coils on N2. If you wanted to step down or turn down the voltage, then we're going to have less coils on N2. So we can convert between any set of voltages that we want. Also keep in mind that Ohm's law is also going to have some conservation law applied to it.